morning, everyone. Hi. My name is Jasper Kanetake, and I'm a security researcher at Beosin. I'm 27 this year, and I joined Beosin last year. I was graduated from University of British Columbia, and I started my cybersecurity career in my second university. I founded my first cybersecurity club in university, and started my Web3 journey in 2017 when I joined the EDCon conference and I met Vitalik in person. So my job title right now is security researcher, which I found to be a funny title because nobody really knows what it means. I would like to think myself as an engineer with an interest in exploit development and research. So to put it simply, just to understand things and to break things in an unexpected way. Okay, so can I get a quick show of hands? Like, how many people here have some basic knowledge in object-oriented programming language? Okay. Okay. So for those people with some experience, this lecture will be quite easy to follow. And the seminar will be divided into 2 days. And the first day will just be some basic concepts and some programming parts. And the second day will be mainly security focused. So we'll talk about like how to analyze incident, how to do formal verification, and some like introduction for blockchain CTFs. Sorry. Huh? Okay.
Some of them are saying too soft.
Okay. Yeah. Okay. So let's dive in. Smart contract and Solidity basics. Oh, like, do you have any questions about me and my company? Not yet. Okay. Okay. So the syllabus will be divided into 7 parts. First, we're going to talk about basic structure of smart contract. And then we'll introduce some data types. And then we'll talk about function and function control structure. Then we will do some examples in error handling. And we will introduce special variables in Solidity. Finally, we'll use an online IDE remix to deploy contracts.
Hi, sorry.
Yeah.
Are the slides available online or not?
I think it will be available online.
After? Oh,
Yeah.
Okay.
Okay. Okay. So in Solidity, a contract is similar to a class in an object-oriented programming language. So it infers that the contract can inherit other variables from other contracts. And there are 6 important declarations in the smart contract. First, there's state variable. State variables are values that are permanently stored in contract. We usually use state variables to store account data. Second, there are struct types. Struct type is a custom type. It is the only custom type you can define in Solidity. That we can use it to group several variables together. Third, there's enumerator types, or enums, as we put it simply. Enumerations can be used to create custom types, consists of constants. So usually they are from the same type, unlike struct types. Fourth, there's functions. Functions are the smallest unit for constitutes an execution unit for business logic. And then we have function modifiers. Function modifiers can be used to restrict permission and to improve the semantics of functions. Okay. Then we have events. Events is an interface, is a human-readable interface that connects humans with the interface of EVM logging function. So we can use events to tap into the rich function of EVM checking and logging. Okay. So on the left side is a simple smart contract. And on the first line, it defines the compiler version of Solidity, pragma Solidity, caret 0.8.0. And it means that the compiler version should be greater than 0.8.0, but not newer than 0.9.0. So why do we need to constrain the compiler version? Because Solidity compiler is constantly upgrading. We need to make sure that our code is compiled with the right compiler version to avoid future bugs. For example, Solidity compiler version before 0.8.0, they don't check for integer overflow and underflow by default. Therefore, developers using old compiler versions must be careful to implement their, for example, safe math library to make sure that the overflow mistakes don't happen. And the third line is an import statement. The import statement will import other files into this smart contract and other global variables. It also recursively imports the file. For example, the file is imported and the file imports other file. So all those files will be imported. It is recommended to use a namespace because otherwise you're going to confuse the variable names. And it also supports backward compatibility. On the fifth line, it's a sort of a definition of a contract. The contract keyword means the definition of this contract, and the name is simple storage. We follow the convention of upper camel case in contract name. And on line 6, there is a definition of uint. Uint is an unsigned integer, and we define variables this way. The variable name is defined is following the convention of lower camel case. On the 8th line, from 8th line to the line 13th, is a definition of a struct called voter. So as we can see, it contains many different types: uint, boolean, address, and another uint. On line 15 is a type enum. The name state is the name of the enum is state, and it contains 3 possible values: created, locked, and inactive. Okay. On the line 16 is our custom version of event. Contract functions in contract can emit events to signal to have this event be recorded in blockchain to make it for easier data collection. For example, there's a dashboard called doom.xyz. You can filter events and have some really cool data research. On line 18 is a start of a definition of a function modifier. As we can see, the name indicates what it means, only setter. It has a require statement that makes sure the message.sender equals setter. So otherwise, if the message.sender is not equal to setter, the transaction will revert and no state change will occur. Other common function modifiers such as only owner or only the multi-signature address of DAO to have the permission control. On lines 26 is a start. We start defining functions. So just briefly introduce how to read this. Function set uint x means it takes in a parameter of a uint x, and the visibility is public, means anyone can call this function. And it returns a value of uint. In this case, it returns the value of our previous defined global variable, stored data. And the get function is public, and the visibility is view, means it will not have any change on the state of blockchain. It just returns, it seems similar to a getter function. And the function abort means that we don't know the implementation details of this function, but we know that only setter can invoke this function. And on line 40, our previously defined event is emitted. So we can view in the blockchain explorer such as Etherscan to see that this event is emitted with the parameter. Any questions about data types or about the basic structures? Okay, let's talk about data types. First, the most important thing is integers. There are two types of integers in Solidity. One is unsigned integers and one is signed integers. Unsigned integers means positive numbers ranging from 0 to 2 to the power of 255, 2 to the power of 256 minus 1. And the signed integer, because we need to store the signs, whether the number is positive or negative. Therefore, the maximum number is 2 to the power of 55. There are also special variables reserved in Solidity to represent those numbers. For example, the uint underline min is corresponding to the minimum value, which is 0, and the uint underline max is the biggest unsigned integer possible. So that is 2 to the power 56 minus 1. Also, the integer also has the same type of special variables. We need to be very careful about the range of our variable because it might cause some overflow. Solidity does not have floating numbers. So what if developers want to use floats? For example, we can use an integer. We can custom define an integer called precision, and we use the former 128 bits to store the integer part of it, and the last 128 bits to store the digits. Second data type is Boolean. Booleans are just literal constants and can be true or false. And the third is address. Address type stores a 20-byte value. It is the size of a typical Ethereum address. As we can see an example here, and I believe anyone who has a crypto wallet will know what an address looks like. The fourth part is the binary type. Binary, so we define binary type by typing bytes and brackets, angle brackets, m. M is the size of bytes. The most commonly used bytes size is byte 32. M size is within the range of 0 and 32. Next, we have enum. Enum is a finite number of optional values, generally declared as enum and custom enum names and curly braces. So this is an example called state. That is an enum that has 3 possible values. This one's a little bit complex. It's called tuple. And tuple is a list of objects with fixed number of elements. So we can see there's uint x, uint y, and integer x. So they can be different types. And during our development, we usually use tuples to receive return values from functions. We don't need to specify every single element in tuples when we try to give values to the elements. For example, we can see the last one. We only use the first value and give it to our variable data.length from the return value of function. And we omitted the second and the third one. Or to make the code more concise, we can give values of two different variables at the same time. For example, the first line, we give uint x the value of 12, the Boolean y the value of false, and the integer z the number of -1.
Sorry, I have a question.
Yeah.
What happens to the other elements that are not defined and not specified? Do they take on default values?
Yeah, they will take on default values. Yeah. It's similar to like Python programming, if you had experience. So now let's talk about struct. Solidity provides a way to define new types in the form of structs. So as we discussed before, this struct voter has some very like layman terms that define like the properties of voter, for example, weight, or whether he voted or not, and if he has a delegate address, or what's the value of his vote. And struct can contain multiple variables and can contain even mappings and array. For example, the last element of this voter is actually an array. Okay. So let's talk about array. Array can be categorized into two types. One is fixed size array, and another one is dynamically sized array. A fixed size array is an array of m. M is the size of m elements, and m is greater or equal to 0. For example, in this example, there are two uint variables in this array, and this array name is b. So the dynamically sized array is more flexible. Bytes is a dynamically sized bytes array, and we usually use bytes in Solidity to store call data. String is another type of dynamically sized array. And we can also define our custom typed array. We can first write our type first, and then the square brackets, and then we don't need to specify like the size of the array. It just means that there are dynamically a number of elements in our custom dynamically sized array. So in this example, there's a dynamically sized array of uint. We don't know how many elements are there, but then in the runtime it'll be figured out. So now it's the mapping. So we usually talk about cryptocurrency as money, but in Solidity it is actually not money. It's just a mapping. So it means like, for example, if I have a contract and ERC token, then a user's address is mapped to a uint value of uint 256 called balances. And when you query this mapping, you can get user's balance. So the user's money is actually completely stored within this contract. And the smart contract can decrease and increase the value. It's just numbers. So there's no concept of money in the smart contract. We'll talk about Move, and we will see like what would be the difference between Solidity and Move. I think tomorrow or at the end of today. Mappings are similar to hash tables in other function languages, and they are virtually initialized, such that every possible key exists and is mapped to a value. In this example, the address is key, and the Boolean is value. Okay. Now let's talk about function. Function is probably the most important unit in Solidity contract. A function is built up by function identifier, parameter, function modifier, and function return value. So let's see how we can read this. The function keyword means the start of function. The parameter types means what kind of parameters are passed into this function. And the function modifier will limit the function scope. We listed examples here: public, private, internal, and external. And each of them have different visibility. Also, they are pure, constant, view, payable. Payable is interesting because the function needs to be payable in order to accept Ether from the message.value passed in by user. And it returns whatever return types you define it. In the example, the function name is set. it takes in a parameter of u in x. The visibility is public, and view means that anyone can call it, and it does not change any state in the contract because it's view. And it returns a Boolean value. It always returns true in this case. Now let's dive into the function visibility specifier. The function visibility specifier specifies the behavior and calling rule of the function. The common modifier in Solidity are public, private, external, and internal. Public means it's visible externally and internally. Internally means it can be invoked by other functions in this contract. Externally means it can be invoked by other contracts or any user EUA address. For example, this add function is public. That means anyone can call it. Private means it is only visible in the current contract. So this is a convention in programming. So we use we have a public access point called add, but then the detailed implementation is private and it's only visible within this contract. So the first function underlying add is a private function, and it's invoked by the public add function. This encapsulating will protect the vulnerable function somehow. External means it is only visible externally. That means the functions within this contract cannot invoke this function. It has to be message call. But if you want to invoke this function within your own contract, what do? You specify this .func. This represents the current contract's address. Internal means it's only visible internally. Okay. And internal can decorate both variables and functions. We can define a variable called internal that has the modifier of internal. So this is the payable modifier. Functions and addresses declared payable can receive Ethereum into this contract. If in a contract there's no payable function and received Ether, and the function will not go through. And that's why a lot of contracts have the default payback function, which will just receive Ether. This will create other problems, as we will talk about in the vulnerability session. Yeah, so it will report an error when function does not specify payable, but transfer Ether to this contract. Now, let's talk about function modifiers. Modifiers can be used to change the behavior of functions in a decorative way. For example, you can use a modifier to automatically check for condition prior to executing the function. This is a very classic modifier called onlyOwner. That means it will basically intercept the function flow and check first if the message.sender is actually owner. And if the message.sender is not owner, this entire transaction will revert. Modifiers are inheritable properties of contracts and may be overridden by derived contracts. So as we saw before, we can use import to import other files into your contract, and you can override the previous defined modifiers with your custom logic. So modifiers usually define marked as virtual, which means it can be overridden. Now let's talk about constructor function. This is the constructor basically means you're creating a new contract. On versions before 0.4.24, you can create a function with the same contract name and quickly assign it the parameter of this contract. For example, the contract name is test, and we have a function had the exact same name as test. And we pass in parameters, we initialize this contract. It is, however, deprecated since version 0.4.22. Constructor keyword is actually used right now, and we should stick to the new convention. The function plus construct name, the constructor, and we pass in the parameters to initialize, and other logic remains the same. Now let's talk about function overloading. Unlike many programming languages, Solidity can have functions with the exact same name, but different parameters. As we can notice in this picture, there are 3 functions. All of them name is add, but they take in different parameters. The first add takes in 2 uint 256, and the second add takes in 1 integer 256 and another 2 integer 256, and the third add takes in 3 parameters, 2 uint 256 and a string called data. In our function test, our uint 256 test 1 uses the third function add. The Solidity can determine which function to use by the variable types we pass in. And the second, test 2, we added C and D together. C and D are both integers, so the second add function will be used. And our return value is actually a tuple. Functions with the same name can reduce the problem of naming more functions with the same exact function. Oh, any questions regarding this content? Okay, function control structure. Solidity contract is executed sequentially from top to bottom. For example, in our function test, the first add function, the function flow goes like this. So in order to get the value of test 1, we invoke the third add function, and that's the first step. And the test 2, we use the second add function, and then the values will be returned. So it's just from top to bottom. Control flow can be altered by using different methods. There's if, else, while do, for, break, continue, return, and the ternary value. It's similar to JavaScript and C. In our example, the first block is an if-else block, and the second block is the while block, and the third block is the for loop. We need to be careful to not to have the for loop and while loop have some user-controlled elements. For example, if you have a user array that's very long and you for loop it, it might reach the gas limit, and the transaction will not go through actually. And the fourth one is just a ternary operator. It's just a simple logic that fits in one line. With the exception of switch and goto, most control structures in JavaScript are available in Solidity. Now let's talk about error handling. Solidity uses state reverting exceptions to handle errors. State reverting means that if a function is reverted in the middle, then all the previous change will be discarded in the blockchain. There are some keywords that we can use to perform error handling. Require keyword reverts if the condition is not met. It is to be used for errors in inputs or external components, and it's probably the most commonly used one. Assert will cause a panic error and thus state change reversion if the condition is not met. It is usually used in development phase and usually used for internal errors. Revert will abort transaction and reverse state changes. Error is a new keyword. Starting from Solidity version 0.8.4, there's a convenient and gas-efficient way to explain to users why an operation failed through the use of custom errors. It is very helpful because in a traditional require, you just see the function revert, you could just see the transaction reverted, and you have to go through the stack to find out what went wrong. There's an outdated keyword called throw. It just throws an exception and fall back. There's no error message whatsoever. Therefore, it's not used anymore. In this example function test, first line, we use a require statement. If a plus b is greater than 10, and then the function will continue. But if a plus b is not greater than 10, then an error will be outputted to user. Assert will make sure this condition is met. A and b is always greater to 10. And this revert will just revert if n b is 10 because it will goes into the if block. Solidity has many special variables and functions, unlike other programming languages because of the nature in blockchain. Here are some special variables. Block.gasLimit is a uint value that represents the current block.gas limit. Block.number is another uint value which represents the current block number. Block.timestamp is a uint value that is seconds since Unix epoch time. You can use some online converting tools to conveniently convert the block timestamp to human-readable forms. Message.sender represents the sender of message. It is in the context of current call. Solidity has delegate functions. That means an EUA address invoked in the contract, and the contract invoke other contract. In this context, message.sender is actually changed to the contract invoked by user in the first place. Message.value is a uint value that is number of ways sent with this message. Message.sig is a 4 bytes data, the first 4 bytes of call data. It is the function identifier. The function identifier is actually the keycheck 256 hash of the function with its parameter, and we just take the first 4 bytes of call data. So for example, if you are reading transactions on Etherscan, and you see this unknown function that has this 4 bytes put as unknown, and I can show you quick ways to look it up on online databases. Okay, what happened? Sorry. Sorry, I can't project my Firefox screen.
Oh, do you want to send here? Maybe it's faster.
Okay. This one, but it's not on the screen yet.
Oh, you can change desktop.
Desktop. Okay.
Also, I think I've sent the slides. There's a link to the slides to everyone, to your email address, so you may check it. If not, I will write down the shortened link on the whiteboard later on. Thank you.
Okay.
群俊，你可以吗？你们去那边。你会帮我剪面去那边吗？
4 byte.
对，他的那个 Firefox project 不到上去。I can try projecting your laptop first.
It's okay. I think I got it.
Okay.
Where's the Mac? Okay. So let's just take a random example on Etherscan and try to find out the function identifier. So here we see that the Etherscan already have the method function identifier being interpreted already. But there are times that the function is unknown, and we see the method ID. We take this ID, which is the first 4 byte of call data, and we can input into online database. This is an online database maintained by Sam CZ Song. He's a famous security researcher, and I think his database is better than the other ones. So we can see we input the hash, and the name of function and what parameters it takes will be outputted. Here is another example of interpretation. Oh, so this website is actually offline right now. So, but the first actually worked. Let's see. Sorry, can I switch back to my computer?
Choose VGA.
Choose what?
VGA.
VGA? Okay.
Yeah,
Sure. Okay. The next one is tx.origin. tx.origin is the center of the transaction. It trickles down to the bottom of the full call chain. That means it's always an EOA address, not the smart contract. So it's, we have to be careful with the difference between message.sender and tx.origin. Next, we have block hash. Block hash takes in a UIN number of block number. So we input our favorite block number, and it will output the hash of that given block. But it only works for the 256 most recent recent blocks. Block hash works in the same way. The key check 256 is a commonly used hash function in Solidity. So how we compute the function signature is we use this hash function. And it returns the value of bytes 32. SHA-256 compute the SHA-256 hash of the input. Keycheck 256 is similar, is exactly the same as SHA-3. It's just a different calling name. And the RIPE-MD 160 returns only a 20 bytes long array. So we have to be careful about the difference. One is byte 32 and one is byte 20. The EC recover function is a very interesting function. It fulfills many business logic. For example, you can use a signature to verify if the owner of the assets has approved spending power to another address. It takes in parameters bytes 32 hash. Hash is the signature, and the uint 8, and some 3 other values, V, R, and S. It will verify the authenticity of the signature. And however, it will return 0 on error. Successful execution of this function will return the address that's associated with the public key. Now let's talk about remix contract deployment. Well, can I get a quick show of hands? Like, how many of you have used Remix before? Okay, so Remix is an online IDE with very intuitive user interface. I think it's probably the only graphic deploy that has graphic user interface. But we're gonna introduce it as our first tutorial. So it is recommended by Ethereum, and it's very easy to use. It's virtual, and users can quickly deploy and test smart contracts. We can open Remix by going to this browser, going to this address. And just a quick introduction. The leftmost panel is the icon panel. There are icons that represent different functions. And the second part is a side panel. Side panel is basically a layout of your workplace. You can see your contracts file and directories there. And the panels on the right-hand side is code panel. It's main panel. You can there's syntax highlighting, and you can put your code in there. And the bottom panel is terminal. It will display the results of interactions. For example, whether the transaction reverted or not, how much gas was spent, etc. You can also run scripts on the terminal. So when you click on the first icon, you can see Workplace is created. There's some default contract sample code. We can view this code. And under the folder scripts, there are deployment scripts. It's written in TypeScript. We can also deploy scripts in other languages, for example, Python, or any language that you prefer. Remix IDE will intelligently confer what compiler version to use when we choose compile. Click the compile button on the left and jump to the compiler function. At compiler, you can select the compiler version by yourself, or it will be chosen automatically. And we can compile our contract. I think I might have some problem with my computer, so I can't really demonstrate how to deploy on Remix, but it's very straightforward as everything is in graphic user interface. We'll look at a sample contract later just to review the concepts we studied today. When a new contract has been deployed, it'll be up here, like at the right bottom side. And we can interact with the contract. We can call functions, and we can pass in values to initialize. In this case, it is deployed in Solidity VM. You can deploy these contracts in testnet, mainnet, or your local node network. Solidity Remix has a default function called VM. So this contract, the deploy contract just exists in this Solidity VM by Remix. The address is predetermined, and you can select the address by clicking the button over there. In Remix, it is also possible to directly interact with the deploy contract. For example, here, in our deploy contracts, we call the balance of, and we can get the balance of the tokens. Here we can see the result of the calling transaction. It is successful, as you can see the green tick symbol. Okay. So our company is a company that's focused on smart contract security audit. We provide smart contract auditing and also monitoring service to various cryptocurrency projects. In addition, we provide asset tracing and recovery service to, for example, people who lost assets or people or exchange who want to comply with the anti-money laundering requirement, then we can use our alert system to make sure, for example, if there's a sanctioned address sending assets to exchange, we can alert them and make sure that they comply with whatever regulations their government require. Sorry. So this is just a sample contract in my local machine that I want to show to review some concepts.
Which one?
This. What happened? Yeah. Sorry. Reason? Why? Test.
Let me get help from my colleague.
Okay. Oh. It's here.
然后把它这个头去那个它再这样举上去。
I want to project my. Okay, it's on there. Okay, thank you. Okay, check it out. Where is it? Where is it? Okay, can I see it? No,
We need to check.
I don't see my cursor.
The cursor is at the left.
Oh, left. Okay, click. Drag. Okay, cool. Okay.
You can enlarge the font size.
Okay.
So
I think so.
everyone can see it.
Can anyone see the characters here? Okay. So let's just take a review at the concepts we studied today. I know it's a ostensibly complex topic, and but we need to understand the basic structure of Solidity contracts in order to understand the security of it. First, this contract name is actually storage. It's a default contract storage. I just modified to incorporate some of the concepts. For example, the bytes 32, the name of the bytes 32 variable is byt, and it's actually 1 byte. So actually it can be defined as byte 1. It's a hexadecimal 16. In this context, the other parts will be prefixed with 0, the default value. So there actually be a 32 bytes long array, but only the rightmost, the lowest part will be 16, will be filled. Next one is line 14. It's an enum value, and there are 3 possible values for this enum called state. On line 16, it's actually a custom-defined struct called exmp. It contains 2 variables. One is string called name. Another one is uint256 called value. On line 21st, we define a fixed-sized array that takes in uint256 value. It has a length of 2, and this array name is b. On line 22nd, it's a dynamically sized array of uint256. The name of the array is c. On line 24, it's a mapping. So we basically map the address to exmp, which is our custom-defined struct. The mapping's name is log. Mapping in Solidity is actually a getter function. You can pass in the address and it will return the exmp. 26 is a function named call. The visibility of it is public. It's pure. That means no state change will occur. It returns 2 uint256 values. line 27 is actually a tuple. So we give the value 1 and 2 to this uint 256. It should be x. And another uint 256 y. So x has a value of 1, and y has a value of 2. And x, y's value will be returned as the return value of this function. Do you have any questions regarding this code? Or any parts that you're not very clear? No? Then have a little quiz. So based on the concepts that we discussed today, like what kind of security problems that might exist in Solidity contract? Which structure is vulnerable in your mind? So just use your imagination and see like where bugs could be. Oh, sorry. Anyone? I don't know. Okay.
Anyone want to give a try?
I have a question.
Okay.
I'm just very curious about why in Solidity the function name can be same. I mean, I know
Yeah.
For traditional program, maybe in Python, the function name cannot be same.
Yeah.
In smart contract in Solidity, it can be same. So is this a possibility? Maybe can be a security bug?
Yes, actually, same function name reduce developers' work to come up with different names when implementing functions that just has the same basic needs. For example, add is just addition, right? But of course, when you pass in different types of variables, then you must implement the logic differently. So there will be confusions if developers, for example, not view the parameters carefully, and they use the wrong type of function for their purpose. For example, if they try to use add and then they pass in the wrong variable type, it might go down to a different function. Also, it will cause confusion. Those functions were defined not being virtual, so they cannot be overwritten. And if the file is imported by other project, then it's very difficult to trace back and see why there are 3 add functions and how to implement them correctly. So it actually creates some overhead in terms of integration. And as we can see, it's a common pattern in Solidity. It used to be the constructor. Remember we talked about constructor. Constructor used to have the same function name as the contract name. And there was a time that there was contracts that's just being initialized over and over again, and this will, for example, in the initializing function, the owner address will be set to the message.sender, and if a malicious actor invoked initialize over and over again, or maybe like after the original deploy invoked it, then the malicious actor can take control of the contract and become the owner and potentially do some really bad things. Does that answer your question?
Yeah.
Thank you. Yeah.
You mentioned there's a function modifier,
Yeah.
and it can be overridden.
Yeah.
If there's another something on top of that, so that
Yeah.
could be a source of bug because somebody could overlook that.
Yeah.
Overwriting authority.
Function modifier can be overridden. That is within the code of contract. So it has to be defined by developers. And I will briefly introduce like why this feature is introduced. So modifier is virtual. For example, the Open Zeppelin is a security company that has come up with lots of secure implementations of sample contracts. For example, there's a contract called ownable.sol, which provides a template to have a fine-grained control of owners. But developers, they have different needs, right? So for the modifier of owner, they can override the Open Zeppelin version of only owner modifier and add their own custom logic. So in this case, it's not going to be vulnerable externally. But of course, if developer implemented his logic wrong, then there will be bugs for sure. Okay. Does that answer your question?
Yeah, sure.
Okay, thank you. Any other question? Yeah.
Yeah, so is there a reliance on the tx.origin? So if a attacker actually uses that to have a withdraw function of something, then it can attack, the phishing can occur or something.
Yeah. So actually, the tx.origin attack is related to phishing attack, as you mentioned before. Why is it? tx.origin actually trickles down to the bottom of the call stack. It goes back to the original caller. So imagine a malicious actor created a malicious contract, a phishing contract. He can use like social engineering, for example, a phishing website or some email to ask the victim to interact with his contract. For example, he can say that if you interact with my contract, you can get an airdrop of like how many tokens. Then when the user interacts with his address, the malicious contract can pass in this transaction and call in another contract. So if the target contract uses tx.origin to authenticate the caller, the target address will think that the victim initiated this transaction. And for example, if the victim has money in a vault that's in the target contract, then the target contracts might think, oh, this victim initiated the transaction, and then they can just give the money to the victim. But in fact, the victim is phished, and the attacker contract is actually the one withdrawing the money. So the attacker's contract will get the money on behalf of victim. And that's how the tx.origin was abused and still abused today. The best way is to use message.sender for authenticate, but have to consider the case of delegate call. Does that answer your question?
So you mean tx origin should not be used?
tx.origin can be used, but tx.origin can be used for sure, but they are not supposed to authenticate people.
Okay.
Yeah. This is voting.
Well, other than authenticating people, what else
This
does
one?
the tx origin do?
And tx.origin can output the value of who actually initiated this transaction.
Oh, okay.
It might be used.
Shouldn't be used as authentication.
Yeah.
It's just providing information. Is
Yeah.
okay.
It should be. It's sometimes useful for the business logic, right? But if you use tx.origin to authenticate, if this user really initiated the transaction, it might not be the case.
Okay.
Yeah.
The message.sender is the person that called the function.
Yes, but in the case of delegate call, the message.sender is actually the contract that used the delegate call. For example, here's a user. The user is tx.origin. The user calls the contract.
Yeah.
The contract uses a delegate call to call another contract.
Yeah.
And this contract will see message.sender as the contract, but not the user.
Yeah.
Yeah. And in terms of authentication, there are different ways. For example, verifying signature or use message.sender. And yeah, there are more implementation coming up. For example, you can use the special function that I mentioned, EC recover, to get to make sure that the user actually signed the transaction using his private key. Yep.
Thank you.
Unlock. Okay. Yeah, unlocked. Yeah, just to add up a little bit, because it reminds me of a recent incident on multi-call. Sorry, this is time. Yeah, a recent incident in multi-call that tried to use the EC recover to authenticate if the user actually has signed the transaction, have approved the spending or not. But the WETH is a contract, a wrap ether contract, does not have this implemented, and have a fallback function that just return true. So therefore, like, there's no way for the multi-chain contract to know if the signature is valid or not. But when they add contracts to whitelist, they did not consider that. So they mistakenly add WETH contract into his whitelist. And some malicious attackers use this method to drain funds from other users. And the multi-chain thought that other users has proven attackers to use their contract, but in fact, no, the attacker just used a zero signature.